Hello everyone, today let's take a look at QP number 4. It should be pretty simple after doing QP 139. So we basically have 500 ants uniformly placed on a 1 foot string. Each ant randomly moves towards one end of the string at a constant speed of 1 foot per minute until it falls off one end of the string. Now we are assuming that the size of each ant is infinitely small. When two ants collide head on, they both immediately change directions and keep on moving at a rate of 1 foot per minute. So what is the expected time for all ants to fall off the string? So essentially what's happening here is I have my string going from 0 to 1. It's 1 foot long, obviously. And then x sub I, we're going to use that as the random variable denoting the position of ant I. So all these are the initial starting positions of the ant. They're uniformly distributed, right? So each of these are going to be a uniform 0 to 1 random variable. So maybe x1, our first ant, is placed right here. Maybe x2, another ant placed here. Maybe another ant is placed here, right? All 500 are just going to be somewhere random on this string. Now for each of these ants, it tells us that it's randomly moving towards one end of the string, right? So that means that for each ant has a 1/2 probability of moving this way and a 1/2 probability of moving this way. And each ant is moving at a rate of 1 foot per minute. We know the length of the string is 1 foot. So if this ant right here, maybe it was placed at the position 0.8, if it's moving in this direction to the left in this case, well then it would take 0.8 seconds for it to fall off the string if no other ants collide with it. Because the unique thing about this problem is that if two ants collide with each other, then they both immediately change directions and keep moving at the same rate, right? So if this ant right here starts moving at this direction and the other ant's moving at that direction, right, they're eventually going to collide at some point in the middle. And then when they do, it says that they're both going to immediately change directions, right? And then they're going to keep on moving at that same rate. So when they collide like so, this one's just going to kind of bounce off each other and then they're going to start moving like that. But now really the key thing to notice with this whole problem is that when two ants collide basically like this, right, and then they bounce off each other, it's basically the same thing as if this ant just continued going forward and this one continued going in its same direction as well, right? There's no difference between them bouncing off each other and them kind of just passing through each other. So furthermore, as this ant keeps on going and it collides with another ant, again, it's pretty much just the same exact scenario as if they bounced off each other, as if they passed through each other, right? And now they're going to keep on going like this, and it's going to collide with this ant, and right? And then they're going to keep on going in their same directions, essentially. And then these two are going to collide. They're going to keep on moving in the same directions. So because we can think of these ants as kind of just passing each other, right? We define another random variable ti, which will just be the time that it takes for ant I to fall off the string, right, given whichever direction it's going. That time for ant I to fall off is purely a function of basically what position the ant starts at and which direction it ends up traveling in, right? So if we look at the time to fall off for our random ant, let's say it's this one right here, right? T sub I is going to be equal to x, right? If this distance right here is x, if it goes in that direction with 1/2 probability, then the distance it has to travel is x. So x with 1/2 probability, and then there's also 1/2 probability that it moves in this direction, right? And in that case, it's going to be equal to 1 minus x with 1/2 probability. And because we know x is a uniform 0 to 1 random variable, right? We also know that 1 minus x is a uniform 0 to 1 random variable as well. So therefore with 1/2 probability we have a uniform 0 to 1, and with 1/2 probability we have a uniform 0 to 1. So therefore t sub I is just going to be distributed in general as a uniform 0 to 1. So the time to fall off for ant I is going to be distributed as some value between 0 and 1. And because we have this property when the ants collide, we can basically just think of that as the ants passing through each other, right? We'll then basically define the expected time for all ants to fall off the string. All we essentially have to do is find the expected value of the maximum time, right, for any ant to fall off the string. So here we're finding the expected value of the maximum of 500 uniform 0 to 1 random variables, which is exactly what we did in QP 139. So we know the formula for that already. We found that in QP 139 part B, the expected value of the maximum of basically n uniform 0 to 1 random variables is going to be n on n plus 1, right? Where n is the number of uniform 0 to 1 random variables that we have. In this case, we have 500. So let's just plug in 500 right here. And when we do that, we get 500 on 500 plus 1, which is equal to 500 on 501. So that's the final answer to this question, right? It's going to be 500 divided by 501 minutes. So almost 1 minute, but not quite exactly.